Okay.
Let's try that with the. Okay, so this does not work. So that's fine. Okay. Hi everyone. I am Sunil Simha. I am a graduate student at UC Santa Cruz. I'm coming to my 5th year now, and I will be talking to you about searching for the source of the excess extragalactic dispersion measure, dark matter, of FRBs. So what are FRBs? So this is a brief introduction of what we can do with FRBs. So starting out with perhaps the most famous FRB detected, the Lorimer burst. So what you see over here is a radio detection of an FRB, where the plot is the frequency of the radio waves coming in versus time of arrival. So you can see in the plot, there's this dark streak, which shows higher frequencies coming in first at an earlier time, and then followed by lower frequencies. So this is a classic dispersed pulse that is characteristic of FRBs. So the pulse itself is pretty narrow. So if you can just squish the line together and add it up in the frequency direction, that's what you get. This is a de-dispersed pulse, and that's an FRB. So why is this happening? It's because the FRB light is passing through plasma, and there's a whole lot of it between us and the FRB. So coming in from the host galaxy, the host halo, the cosmic web, the Milky Way halo, Milky Way ISM, all the way down to Earth. And all of that gas is getting probed by this FRB over here. And the extent to which this thing gets dispersed, so the pulse gets dispersed from this to this, is quantified by this measure called the dispersion measure, which is essentially the electron column density along the line of sight. And because it's an integral, it can be split into these different parts. So you can have a contribution from the host galaxy, so basically these two. You can have something from the cosmic web and something from the Milky Way. So coming now to what we call the McCart relation in the FRB world. Basically, if you expect the lambda CDM cosmology to work, and it's true, you would expect that the cosmic web would contribute a certain amount of dispersion measure as a function of redshift. So there's going to be some gas between us and the FRB at whatever redshift. And so the mean relation is going to be well known. It's entirely characterized by the cosmology. Now, overlaid on this is a probability distribution for each redshift, what the actual dispersion measure will be. So because the universe is not really fully homogeneous, there's going to be some clumpy parts of it. There's going to be parts of it which are underdense. Some sight lines of FRBs get more love than others. So there will be all of these outliers. So at any redshift, you could have an FRB which could have like a very large dispersion measure. But for the most part, you get most of these FRBs or the contributions would be smaller than the mean value, which is the dark line. So that's why the median of the distribution, which is in the dotted line, is underneath the mean. On top of this, you could plot whatever localized FRBs we have at the moment. So localized means, in this case, we know the FRB redshift. So nothing in the FRB signal itself gives you the redshift. We need to go back with optical telescopes and confirm that there's a galaxy there, measure its redshift. And using that, we can say, okay, that is the FRB's host. And that's where the FRB is at. And we have, at this point, models of what the gas distribution looks like in our own Milky Way, which are fairly reliable. So we can subtract that out. So that's what I've done over here. We subtracted the Milky Way contribution, and we can sort of guess what the host might be. It's not really clear, but in this case, I'm subtracting, I think, an even 100 units over here. So dispersion measure is measured in parsecs per centimeter cube. So it's basically column density. So I'm subtracting a number for the host, a guess for the host, and something that is modeled for the Milky Way, and I'm left with what is basically the cosmic web contribution. So you can see that the FRBs more or less align with the thing, but the more astute observers among you will notice that there's a whole lot of these FRBs up here, which I'll come to in just a little bit. But more or less, this is the McCart relation, and this is proof that we understand the universe, and there's no such thing as a missing baryon, I guess. We know the baryons exist, and FRBs are proof that they do exist. So this was a great result. So yeah, like I said, there's all of these points which are not really playing well with their models. So what's going on over there? What is the cause of that excess that I showed you? So all of these data points lying above the mean. So basically, you could have a bunch of different reasons. So one of them being there are for all of these sight lines, there are a large number of galaxy halos coming in between. So if the FRB is going through a lot of CGM matter, it's gonna have a high dispersion measure. It could also be that the progenitor contribution or the host contribution of the FRB itself, the local environment of the FRB is really dense and it's got a lot of gas, and that could give you a large dispersion measure. It could also be that there's a large cosmic web contribution, so a ton of filaments coming between alpha and the FRB. But in many cases, it's not possible to have. One of the first reason basically results in the second one. There's never been, like, at least according to simulations, we cannot have this and not have this. So it's most likely these two. So how do we go about disentangling this effect? We started something called the Flim-Flam survey. So this has been work going on for a while. Basically, we're trying to follow up on FRB sightlines with optical observing. We're targeting field galaxies, hoping to catch all the foreground gas or foreground galaxies so that we can accurately reconstruct what the cosmic web density looks like, and therefore produce a dispersion measure estimate that is independent of the radio observations. And in tallying the two, for a number of sightlines, we can then start laying constraints on how much matter or how much ionized matter is there in the CGM, how much is there in the IGM. So this is perhaps the first time that we can start laying observational constraints on some of these parameters. The observing strategies, basically we have the spectroscopic observations from AA omega spectrograph, which is like, it covers 1.2 degrees. And then we have narrow field and really narrow field spectroscopy. So these two are fulfilled by IFUs and a telescope, like instruments like DEIMOS. So most of my results that follow are from DEIMOS and LRIS observations. So these two mainly probe whatever halos that come really close to the FRB line of sight, and then we can get a good estimate of what the dispersion measure from halos are. The wide field spectroscopy gives you IGM reconstructions mostly. Okay, so we have these 4 FRBs in our sample that are really high up there. We're trying to understand what is causing these. So we have observations. We have DEIMOS and LRIS slit mask observations for galaxies that are fainter than 22.5 mags. And for one of these fields, we even have a Muse data cube. So that gets us really a good detail or with the nearby galaxy. So we can really say how much matter is between us and the FRB for those. We also have, of course, the AAT or AA omega observations. So the methodology is pretty simple. We start with the foreground galaxy, we identify it, get its redshift. We then come up with a halo mass estimate. So this is a two-step process. Once we get the stellar mass estimate from SED fitting with whatever photometry we have for that field. Once we have the stellar mass, we can then go to halo mass using an abundance matching relation. So we get halo masses this way. We already know the impact parameter once we know the redshift. So once we have the halo mass, we can then say, okay, the gas distribution on average is going to be in a certain way. We have models for this. And so if you have a gas distribution model, you can then say, okay, this halo will contribute this much dispersion measure. So there's going to be so much electrons which coming in from this halo between us and the FRB. So just repeat this process for all the foreground galaxies until you have a good model of like, or like an understanding of what is going on in the field. So this is what it looks like for one of the fields. So this is 190714, the one with the Muse data cube. So first we just identify all the stars and really distant point sources that don't really contribute. Then we of course get the background galaxies. Again, they don't do anything for our science. And then the foreground galaxies. So over here, the galaxies are color coded by how much dispersion measure that they're contributing to the line of sight. So you can see a whole bunch of these galaxies that are really close by, which contribute quite a bit to this particular line of sight. In fact, if you compare what the dispersion measure contribution from each of these individual galaxies is as a function of redshift, so you just, you could think of it this way, you go from redshift 0 to the FRB redshift, and each time you encounter a galaxy, you add up the dispersion measure contribution. That's what this plot is. And you compare it with what the average value would be for an average sight line in the universe. So that's the dotted line. You can clearly see this excess over here. So this sight line is clearly having an excess of field galaxies that are contributing greatly to the FRB dispersion measure. In fact, you can play another game and say, okay, well, what is the IGM contribution? And then if you assume the sight line is average, well, in this case, it's not really, but still, if you assume that and add up an average IGM contribution, you could just compare it to the cosmic web contribution average, and you still see that it is pretty high. And in fact, it can nearly well account for the FRB dispersion measure, which is excess. So this is one such sight line. Not all sight lines are like this. 210117, this FRB has got very little contribution from the foreground halo, so pretty much nothing really. So there's a lot of nothing over here. So most of this contribution must come, therefore, from the host galaxy. So there are interesting things to be learned. So like this, I have analyzed the other two fields as well. And for those fields, I do find that the host contribution is most important. So 3 out of 4 fields, we see an excess contribution coming from the host. So this starts laying good constraints on, so if you start doing this for multiple galaxies, you can get a distribution for what the host contributions would be like. And also, you know, over 30 sight lines, we can then finally start saying things about the cosmic web and how much gas is distributed where and which components. So that's my work. Thank you for listening. I'm happy to take questions now.
Okay, but I just have time for one question. Go ahead, John.
So what about the boring answer? And the boring answer is we don't understand the Milky Way.
Oh, we understand the Milky Way pretty well, I think. So we have, that's why I was able to subtract off the Milky Way contribution. Because we have maps of the dispersion measure or the electron density from pulsar observations already. So we can reliably subtract that for the ISM.
But are they, I guess, are they close enough? I mean, every time we look at small scales at galaxies, we find that there's lots of stuff clumped all over the place. And so you would have to be lucky enough to have a pulsar close enough to get the the nature of my question has to go with the fact that if more than often you're finding that the excess dispersion is from the host progenitor as opposed to the field along the way, that's equivalent in my mind of saying we don't understand how galaxy dispersion measures work, which means we might not understand how the Milky Way.
Well, to be fair, so the Milky Way contribution for most of these sight lines is going to be small because they're not in the plane of the galaxy.
Sure, good.
Right. So that is something that we need to keep in mind. But yeah, we do not fully understand like host galaxy contributions, but this sort of work was one of the ways of getting a handle on that.
Okay, thank you. Thank you all the speakers there.